Hey guys, we'll wait a few more minutes for everyone to join. Okay, hello everyone. Happy Monday. Any questions before we start? Just a reminder that your assignment 1 is due this Sunday at midnight your time. So yeah, midnight your time. My voice is I'm actually feeling sick, so it's not good, but I'll try and talk loudly. Let me know if at any point you guys can't hear me, and I will go over what I said again. Okay, so if there's no questions, let's start back on chapter 3 on randomization. I'm going to share my screen. Oh, there's a question. Okay, sounds good. So I'm going to share my screen. Okay, so if you guys remember, we just finished off last time with internal and external validity. So if he wants to tell me the difference right away between the difference between internal validity and external validity, just as a refresher, you can message me in the chat, or if you want to use your microphone, just a quick little difference between the two. Anyone? Nice. Exactly. Nicholas says the internal validity is the impact being estimated is the true impact. And that's correct. So internal validity is looking inwards within our methodology and making sure that there's validity. So that is dependent upon our assumptions that we need to have causal inference that they hold true in reality. And then he adds external validity is the sample accurately represents the population. So that's also true. So external validity is all about sample selection. So when we choose a sample that we're studying, we want it to be representative of a larger population. And that's really important so that we can make generalization with our analysis. So if we have a really specific subpopulation and we find an estimation, we can't necessarily say that that effect is true for larger population if their characteristics are super different than the average population, right? So those two aspects are both very important in terms of policy recommendation and impact evaluations, because of course we always want to make causal inference. If we don't have causality, we really can't offer any valuable policy recommendations, right? And then secondly, if we do find a causal estimate, but it's only representative of a small population, then it's not very good for policy either, because we can't say if we were to expand the program to the rest of the country or other countries that it would be just as effective. You know, so for that reason, the two are very important. Good job. Oh, COVID. Okay. Okay, so topic 5 is when to use randomization. So in real life, there are some circumstances where policy is being implemented that it's more ideal to use a randomization strategy that's really just making use of a natural, it's kind of like a natural experiment almost, because it's happening anyways. So as an economist, you may as well exploit this. So there's two main situations when it is super efficient to implement a randomization. And the first one would be when the eligible population is greater than the number of program spaces available. So that's like we talked about Progresa in Mexico, which basically had higher demand for the program than there were spots available. So when demand is higher than spots available, it can be seen as unfair to choose who should get the policy or who should receive the program treatment and who shouldn't when everyone is eligible in this subpopulation. So instead of choosing who should and who shouldn't, which can be unethical, it's really popular to use a randomized lottery. So basically, it's completely random within the eligible population who in the end receives the treatment. So when you do have larger population of eligible people than spots in the program, it's recommendable to use randomization. Oh, sorry. Okay. And then the second example is when a program needs to be gradually phased in until it covers the entire eligible population. So that could be something similar as the first example. So you have a large population that needs to receive treatment. But maybe instead of giving everyone all of the treatment at once, we can use some sort of randomization design where we only treat 1/3 of the eligible population to begin with, and then leave the other 2/3 as a control group. And then we can gradually give treatment to the other two groups because they're both eligible too. So that's the only fair thing to do. So we treat the first group and compare them to the second two groups. And then we can add the second group into treatment. So give the second group treatment and then compare that group to the control group, and then finally give the third group treatment. And then when the last group receives treatment, obviously there's no compare group or control group, so we can't do an analysis, but then it's kind of nice because then everyone's getting treated and it's a lot more ethical. And also you're able to do a randomized experiment by kind of, what is the word? Kind of changing times with which they receive treatment. Okay, any two questions on those two instances? You guys, I'm not gonna make it next week. I have COVID. Your professor's gonna die. Okay. So So to be able to initiate a randomization among a population, you really need to know first what unit you'll randomize at. So this is an implementation question. So normally, oh my God. Normally when we think about randomization, um, we think about at the individual level. So I go to the hospital, you don't. I receive treatment, you don't. So everything we have so far thought about at the individual level. However, you might also want to randomize treatment at the household level or the school level, or it could even be like hospital, village, distrito, something like that. Um, and there's different reasons. Oh my God. There's different reasons for choosing a different level of randomization than just the individual. So some things that should affect your choice. Well, for one, sometimes randomizing at the individual is really nice because when you choose a larger level to randomize, you're going to need an even larger sample size to obtain enough statistical power. So basically, when we're randomizing over just one group, so one group receives treatment and one's control, sometimes within a group there's a lot of correlation between each individual outcomes. That's going to make it harder to measure the true effect. So when you do randomize at a larger group level, you're going to need to add more groups to compensate for the statistical power. And then also, an argument for using bigger groups is spillover effects. So we kind of talked about spillover effects before. So for instance, say that I received a treatment effect, and the treatment was that they gave me a box of food to give to my kid or something like that. So every month I received a box of food, and that's supposed to help my child's nutrition so he can go to school and pay attention or be healthier. There would be a spillover effect if, say, my household was a treatment and my neighbor was a control group. Well, maybe there's too much food that my kid can't eat, so I decide to share with a neighbor, or that just the kid doesn't like the food, so I give it to her. So if there's any spillover of the treatment from the treatment group to the control group, that will bias our estimates, right? Do you guys know why that would bias our estimates? Well, it would bias our estimates because then if the control group is receiving the treatment effect as well, then we're not comparing, we don't have a valid counterfactual. Because recall that the control group, we want it to have the outcome, the same outcome that the treatment group would have had in the absence of treatment, right? So there has to be no treatment given to the control group. So if there is a spillover effect for that reason, our effects are going to be contaminated and it will be biased. So before you even randomize, you can try and account for this by randomizing at a larger level. So maybe if you think that there's going to be spillovers between neighbors, that I would share my box of food with my neighbor, you don't want to randomize at the individual or household level. Maybe then you want to randomize at the community level. So there are instances of this. There's an example that we're going to talk about at the end of this chapter, where Miguel and Kramer, they look at the effect of this deworming medicine. So it's medicine to remove worms from your stomach, which can be harmful to nutrition. So they found that when kids were receiving deworming medication, it had positive effects on their peers because worms are spread. It's contagious. So then if a kid doesn't have worms, his best friend is less likely to get them. So for that reason, there was some sort of spillover effect when you randomize this medication at the individual level. So then to account for any spillovers, instead of randomizing at the individual level, they decide to randomize at the school level because kids are less likely to hang out with kids from other schools, and so that would pretty effectively contain the spillover effect. So if you're implementing some sort of experiment, it's very helpful to think about how the treatment could potentially spill over to the control group and try and prepare for that ahead of time by being careful about what level you want to randomize your research at. Also, randomization is more simple on a group level, and that's just because there's less monitoring needed. And yeah, just less monitoring. It's easier to manage from a administration standpoint. Okay. If you guys do not have any questions on that, we're going to move on to topic 6, some issues with randomization, which kind of one of them was spillover, so we already started talking about it. But yeah, all right. Okay, so in practice, implementing a randomization design can definitely face some issues, although it does seem pretty perfect. But for instance, suppose you perform a randomization at an individual level and you put 100 people into the treatment group and 100 people into the control group just by randomization, so they randomly put into each group. Sometimes, unfortunately, even though you randomize, you could find that when you check the balance between treatment and control group, that some variables are not balanced. So the probability that there will be an unbalanced variable will decrease as your N goes up. So as the treatment size and the control group gets bigger, so just your N. But that's expensive, so there kind of needs to be a trade-off between whether to increase your sample or whether you can get a good balance with the sample you have. Yeah, sometimes even though you might perform randomization, there still could be some variables that are unbalanced. This is just, it happens sometimes with the luck of the draw randomization. So we're going to talk about some solutions for that. What I want to say? So sometimes it's not a huge problem. So if you think about your y variable, your dependent variable, if the x that's not randomized, if the covariate that isn't randomized well, isn't super important to the outcome variable, and you can't really think of a convincing way that it would affect your outcome variable, then I wouldn't be too concerned about it being there. You can always just control for it in a regression. So as we talked about before, recall that when we have randomization, our standard regression will just be the OLS. The y is a function of x. But sometimes if you have this variable that's confounding, it's fine to just add it as a control, especially if it doesn't seem that important. However, where you would be really concerned about a variable not being balanced is if it was the y before treatment. So we always in a balance table want to make sure that our y variable is balanced to begin with. So before treatment, our y needs to be exactly the same statistically. If it's not, we would be concerned that there's selection bias driving the difference. So you just have to hope that it's not your y that's not balanced between the two groups. But we'll talk about some actual solutions. The first, as I just mentioned, is control variables. It's the definitely easiest and most common way to control for variables when they're not actually balanced between the two groups. So For example, theoretically, if you have a simple randomized experiment, so just the treatment group and control group, and say your groups are perfectly balanced. So suppose there is no problem with the balance of the variables. You could still control for baseline values of the covariates, which obviously they won't predict the outcomes, right? Because if they're perfectly balanced between the treatment group and control group, it's not going to tell us anything of our y variable. However, sometimes it can be good because it can reduce the variance of the beta. So the beta being the estimator for your treatment dummy. So your DI equals 1 if you receive treatment. Normally, economists don't do this. If you don't have a problem with the balance of the table, they won't add controls just for simplicity. But even still, sometimes if you do have a perfect balance, they might control for the baseline y variable. So sometimes they put in the baseline y variable even if it's perfectly balanced table, and that's called the ANCOVA. I'll write that down. Not in my notes. That's the ANCOVA specification, where it's basically just the regression, but then controlling for the pre-treatment y. Oops, I put that privately. ANCOVA. Okay. So yeah, obviously the reason why adding the covariates wouldn't affect the estimate is because we have a randomized sample, and therefore the only thing explaining our outcome variable should be our treatment dummy, right? In the case that it's an imperfect randomization, you can control for these variables that aren't balanced. But just remember, when the groups aren't perfectly balanced, then it shows based on these characteristics being differently. You can control for these variables, which are observable characteristics, but controlling for observable characteristics doesn't mean that the unobservable characteristics are controlled for. So if there's some sort of sorting between the treatment group and control group based on the difference of your covariates, then there could still be difference. There could still be selection bias and some sort of unobservable variable. So you need to be careful of that. And you can't always immediately say that, well, I have this variable and it wasn't balanced, but since I controlled for it in my regression, we have causality. You also need to think about what unobservable variables might be different than based on those covariates. Oh my God. Okay, yes. So Maria asked if I can repeat what ANCOVA is. Yeah, ANCOVA is just the regression. Oh my God, our simple OLS regression. So y is a function of our treatment status, but then we're also controlling for our baseline y. So I'll write it here in the regression. So it'll just be like y I don't have subscripts right now, but alpha plus beta times d, where d is our treatment, and then plus y, but then t equals before. So that would be their equation, obviously with an error term and then subscripted with i's. Yeah, that's the ANCOVA. And sometimes it's just nice to include because, of course, you want y is obviously the most important variable because it's our outcome variable. So you can control for it if it's not balanced. And even if it's not balanced, controlling for it adds some sort of robustness and also will reduce the variance in your beta for your beta DI, because you would think that the y before the treatment is the most explanatory of the y after. besides treatment status, so that's why it's recommendable to include. But I mean, if you do have perfect balance, I would include just a simple regression first and then maybe a secondary regression as the ANCOVA and just say, look, they look similar. Maybe the standard error is smaller, but it's just a nice comparison. No problem. Okay, so, right, I was saying you can add control variables if you don't have perfectly randomized variables, but just be careful that that doesn't ensure unobservable variables are also balanced, right? Because the principle of randomization is that obviously we can observe unobservable variables by definition, but the argument of randomization is that if we're randomizing observable characteristics, we're also must be randomizing unobservable, right? So if we can't randomize the observable variables perfectly, we can control for them, but then we're concerned that some sort of unobservable variable isn't controlled for, and that would create selection bias. Sandra's calling me. Oh my god. Okay. So yeah, I mean, I already talked about this, but add control variables if you need to. But you might still be concerned that we're not capturing a causal effect. But then that's where it comes in, where you're an economist and you can argue why that variable does or doesn't matter. So that could be a big part of it too. Just justifying that you do have causality is a large part of economic research, to be honest. Okay. Yeah, we talked about this already, just controlling for your baseline outcome. It can be really good because you can reduce the variance and also it improves precision of estimates. Okay. Also be careful, like within randomization, the basic principle is that randomizing is removing selection bias, right? So then you only need to estimate the effect of treatment on your outcome. So you really don't want to overspecify your model. So don't be adding random covariates. It's not going to improve your beta, and it's just going to look like you don't know what you're doing. So just keep it as simple as possible. Add a covariate when you need to, when a variable isn't randomized. Okay, so one way to avoid this problem is even before we randomize to choose which variables are important to us. So we say, I'm looking at the effect of, I don't know, going to the hospital on health. This is our example of the semester because I'm not creative. So before I even randomize who goes to the hospital, I'm going to think what variables are important in affecting our outcome variable, health. So what variables do you think would be important to health? Maybe age, maybe income, maybe physical activity, job. So maybe you choose 4 variables that you think are the most important. And you're going to, I'm sorry. And, oh, there it is. And you're going to randomize on those variables. So I'll repeat that because that was crazy of me. So choose what variables you think are most important in explaining the outcome, and then maybe we can randomize on those variables or within. So that is exactly what stratification is. Stratification is awesome. I'm seeing it a lot more in randomization papers because it is a really good way of ensuring the covariates that matter, they aren't unbalanced between the treatment and control group. So stratification is basically ensuring that whatever covariates you choose to stratify on there will be randomization within that group. Basically, yeah, that's fair. Okay, so stratification. You need to choose the covariates in advance, obviously, because you choose your variables, and then within those variables, you're randomizing within them, right? So instead of having a whole population and saying, you go in treatment, you go in control randomly, we're saying we have our whole population, and then we have age. So if your age is under 50, let's say, or no, say under 25, you go to treatment, you go to control. So it's randomized in that age group. And then the next age group. So whatever within your age category, you're randomized into treatment or control. And that's really precisely ensuring that these characteristics that matter to your outcome are being randomized. And then you can do other characteristics as well. So sex. So all the males are randomized and then all the females are randomized like that. And that really ensures that the covariates won't be unbalanced, but yeah, that's what that means. So it's basically another type of constrained randomization. So it refers to the situation in which strata. So strata you can think of as blocks, or it's basically whatever variables you have are constructed based on your variables. So for example, we have a strata of males that are 25 to 30 that are working as in an office job. You have all these characteristics that you think are important. And so people who look alike are put in one block. And then within that one block, you're randomizing. So yeah, these strata are designed based on the variables of your choosing. And then you do a randomization within each strata. So when we say prognostic variables, that just means they're explanatory to our outcome variable. So we think they're important for that reason. So suppose there are two prognostic variables, age and gender, which we are concerned about for our outcome. From there, we'll split our sample into smaller sample sizes separated by these characteristics, age and gender. Right? So then you have all these strata. You say male age under 18 or male age over or equal to 18. And then same thing for females under 18, females equal or greater to 18. And then you have your two different treatments. So this would be, for example, treated, not treated, treated, not treated. So you can see within each category, these groups are really balanced. So that's good because when we randomize on the whole, say we took this whole population of people and just randomized treatment and control, it's not guaranteed that these two variables will be randomly or balanced through randomization. So this is a really good way of just ensuring that your balance tables will look good at the end of randomization. So yeah, that was an example of splitting a sample into subgroups known as strata. Once they're split up into the strata, we'll randomize. So you can think of stratification as an extreme sample. It's just pairwise matching. So say you put two people together that within the sample, they look almost identical or identical as possible. And you do that for every individual. So every person that receives treatment has an identical person that looks like them that is the control, right? So this would be an extreme example of stratification where you put two people together and then randomly say which one of them gets treated. And of course, that's not just matching, because matching doesn't rely on the randomization. So the benefit of randomization is that when we randomize, we're randomizing observable and unobservable characteristics. Whereas if we already have people that are treated, and then we find people that look like them that are untreated, and then compare the outcomes, we're concerned about unobservable variables. So that's why this randomization using stratification is really more solid. It's because we have this randomization, which is removing selection bias on both observables and unobservables. Just to be clear. I hate matching. Such a pain. Okay. Okay, so then whatever strategy you choose, you need to choose a few variables that you think are most important ideally. Because if you choose too many variables to stratify on, obviously your groups will get smaller and smaller. So it's better to have like 3, 4, 5 really important variables and stratify on those. Okay, so when the same proportion of observations are assigned to the treatment and the comparison in each strata, then the average treatment effect is equal to the difference between the outcomes of the treated of all untreated units. So basically the weighted average. It's the weighted average of the differences within each group, right? So we're taking the difference within each group and then taking the weighted average of all groups, weighted on their population size. Is that clear? What I just said here? So instead of doing the standard regression where we only have one group treated and one group as a control, and then we just take the difference in average outcomes between the two groups, this time think of it as a bunch of mini groups. So within each strata, we have one group, right? And for that group, we have a treatment group and a control group. So we'll take the average outcomes of both and then difference. But then we have that for a lot of strata. So then we need to combine the average differences for all the groups, and that will be a weighted average. So yeah, stratification is a lot more efficient than the inclusion of control variables. This because basically they ensure an equal proportion of treated and untreated are within each strata, and it minimizes variance. So for instance, you could randomize and say one group, say one characteristic, like age less than 18, somehow no one less than 18 got treated, so they're all in the control group. So it's not balanced, and then if you if you control for that, it'll just lose all the variation on that. Yeah, it can be harmful. And then also the same argument as the observable versus unobservable characteristics, the controlling afterwards really doesn't address that as well as stratification. So it's better if you can be careful with your analysis and think about stratification before you randomize. Yeah, so for example, there's an extreme example where you could do a complete randomization where in some blocks there's only treatment or only control groups. So say we randomize on the whole and say for one block age less than 18 is only a control group. Then this block doesn't contribute anything to the analysis when we control for it. So if we need to control for that variable afterward, since it's all in the control group, there's no comparison within that variable, right? So that's why we can actually reduce the effective sample size, because when we control for that variable, there's no variation in it between treatment and control. When we control for it, we're just losing all of that variation within that category for kids less than 18. So that's why it's better to stratify in that case. Any questions? All right. We'll keep going for 10 minutes. Okay, so another reason why stratification can be super awesome is because maybe we're interested in the effects of specific subgroups. So say we think that maybe there's differential effects between females and males. Well, if we stratify on sex, then it's really easy to check that, because we're basically guaranteeing that it's randomized within the age variable. Whereas if we just did a randomization at the whole level and then we looked within the sex, then it's not guaranteed that it's been randomized. I mean, most cases hopefully it will be, but this is just if you're concerned that you want to do this subgroup analysis and you want to be sure that it will be randomized properly at the end. Yeah, also just stratification can be good because we're avoiding the like over specification. So if you choose carefully what variables you want to control for before you randomize, you're less likely to be able to just throw in a bunch of control variables or change your specification to try and get the beta that you want. Of course, this isn't really too common in randomization because the result or the methodology is pretty straightforward, but yeah, it can be more like transparent. Okay, so just recall, so within randomized or the stratified randomization, we're randomizing treatment status within each strata, so within each group. This can mean that the treatment status, it might not be random over the entire sample if different strata have different probabilities of selecting into treatment. So for example, if there's only a certain number of spots available for a program within each city, then the ratio of treatment to control will be based on population differences. So obviously, if there's a certain number of spots for treatment in a small city, there will be a higher treatment to control ratio. If it's a larger city, the ratio will be smaller. So that means that the treatment status is conditional, random, conditional on a set of observable variables, which is the variables that we randomize on, right? So it's not just random on the whole, it's random on the conditional on the set of variables. Okay. Next is cross-cutting design. So these are pretty cool. This is when you use, that's the downside of stratification. Having them random at certain subgroups rather than the whole population isn't necessarily a downside. It just might change your inference a little. So it wouldn't actually be considered the average treatment effect then. It would be average treatment effect conditional on these variables. So, I mean, I don't think that's harmful to the estimate or to your policy recommendations, but it would just change how you interpreted the results, I guess. I wouldn't call it an upside or downside, really. I don't know. I don't think it's a downside personally, but I guess your take too. What do you guys think? No problem. Okay, so cross-cutting design uses several different treatments at the same time. So basically, we're doing randomizations conducted so that treatments are happening at the same time as each other. So for example, if a researcher wants to cross-cut interventions A and B, they both obviously need to have a comparison group. So she'll need 4 groups. So there's going to be a pure control group, so they receive no treatment, and then a group that only receives treatment A, and a group that only receives treatment B, and then a group that receives A and B together, right? So then of course you want to know about how both A and B separately, how are they effective compared to the pure group, and then maybe For policy, they're thinking of, well, maybe it's only effective if you combine the two. So then you can combine or compare A plus B to just A, just B, or peer. And then you can see which is the best to do, whether you only need one isolated or whether it's better to have both together. Okay, we'll talk about externalities in 10 minutes. So I'll see you guys at 7 p.m. I'm just going to pause my screen, but I'll see you in 10 minutes. Okay, we're gonna start again. Is there any questions before cross-cutting design or stratification? All right. So the next problem with randomization sometimes is externalities. So we already talked about externalities, which are basically something, it's basically a spillover effect, but maybe not that the kids are directly receiving treatment, but there's some sort of somehow indirectly repeated affected by treatment. Yes, Nicholas, I'll repeat cross-cutting design again. Okay. So cross-cutting design is basically when there's multiple treatments that we want to test at the same time. No problem. Yeah, there's multiple treatments we want to test at the same time. So suppose we want to test two things, A and B. So it could be, for example, treatment A could be some sort of maybe like giving medical care to pregnant women, and B could be an information session on different ways to take care of yourself during pregnancy. So these could be two different treatments, and we want to test how effective they are independently, and then also whether they're more effective when they're paired together. So maybe there's no point in implementing this medical care if it doesn't come along with the information, so that the woman can't maintain their health throughout pregnancy, or maybe the information is sufficient, or whatever, the combination of the two are better than just one of them alone. So this is what economists want to test sometimes. So if this is the case, we're going to need more groups, obviously, because we need a group A, or a group that is just pure control. So a group that receives no treatment, and then a group that only receives treatment A, so only the information treatment, and then a group that only receives treatment B, so they go get the medical care, and then the final group will receive both of the treatments together. So then this final group will receive the information plus the medical care. And then we want to know whether each treatment was effective alone, which was more effective, or maybe if they're only effective when they're paired together. So this is really the main function of a cross-cutting design. So you can not only compare each treatment group to the peer control group, but you could also, for example, compare the outcome of treatment group A plus B to the outcomes of either A or B, because maybe there's differential effects. Maybe it's better off if you receive both treatments rather than just one alone. So this is one way to test that. And then it obviously would be randomized into 4 groups instead of just 2. So yeah, that's cross-cutting design. We don't see it a ton, but it can be popular, like when paired with information example, you see more often. Okay, so another problem is externalities. No problem. Okay, who wants to tell me or remind me what an externality is? I already kind of mentioned it, but this is like classic economics. What I do affects others. Yeah, exactly. So basically the treatment effect is affecting others, potentially the control group. It could also be affecting other people in the treatment group. Depends. So yeah, for example, and what's this example here actually? So these two authors, Vermeesh and Kramer, found that the provision of school meals to preschoolers at some schools in Kenya led nearby schools to reduce school fees. So that could just be because if this school is offering free lunches, the other schools need to be more competitive, and so they'll reduce prices. So you can see how that could also affect the school outcomes of the control group if they're subject to lower school costs just because of the treatment effect, right? So indirectly, the control group would be affected by the treatment group, which would bias our estimates, and we don't want that. Right, so we all know that if the control group is affected in any way by the treatment, even if they don't directly receive treatment, if they're somehow indirectly affected by the treatment group, they're not a valid counterfactual, right? Because we need the control group to measure the outcome for the treatment group in the absence of change. So this would create bias, obviously. So for example, for this school lunch example, you can see how the treatment effect positively affect the control group, the students. So how would that bias our spillovers? Do you guys think that would overstate the true treatment effect or understate? Understate. Yeah, understate is correct. Well, yeah, it does depend on the spillover, Santiago also, but if we're saying the effect is positive on the control group, so the spillover is positive, then the effect would be understated, because then we have a treatment effect on the treatment group and the treatment effect on the control group. So when we compare the difference, we're not accounting for the fact that the control group was positively affected. So then our true estimate is understated from what it would actually be if the control group was in absence of treatment. But yeah, it does depend. So if the spillover was negative, so if somehow the treatment group's positively affected and that makes the control group worse off, then our effect would be overstated. So it really does depend on what the spillover effect is in general. And that can happen based on, for example, if you have a really small village, there's been cases where randomizations have given some households a cash transfer. So just give all households $1,000, for example, and then treatment groups or control groups, nothing. So if you're giving half of a village $1,000 and the other half nothing, that could actually have general equilibrium effects that would affect the control group negatively. All right, so maybe that could, I don't know, drive prices up in the community, and the control group who received nothing would be worse off. So there are examples of externalities in randomizations that go both ways. It's just important to acknowledge or think about whether there could be externalities. They aren't as common in randomizations, especially if you're looking at a relatively small sample size. Okay, so there's some ways to control for this exposure within randomization. So one way to do it is to vary the level exposure to a treatment within a group. So we already talked about this, but this is like the same as spillover, I guess. You could randomize at the school level instead of the child level if you suspect that a treatment effect on a kid may spill over to his peers. So a second technique is to exploit the variation in exposure across groups that naturally arise from randomization. So for example, these three authors, Duflo, Kramer, and Robinson, they did this agricultural randomized treatment effect where they randomly selected sample of farmers, and then they asked all the farmers the names of three farmers that they discussed agriculture with the most often. So by asking them their like best friends basically, or who they talk to most, this allows them to sort of estimate the externalities by then comparing between best friends of the treatment group to best friends of the control group. Right, so then you can actually measure spillovers, because you would think, for example, say these farmers are receiving some sort of information on the best practices of agriculture or farming, and then they're more likely to share with their friends, then you can compare like the top 3 friends of the treatment to the top 3 friends of the control, and that would be able to estimate your spillover effect. Okay. Another problem could be attrition and randomization, which we did talk about a fair bit on Wednesday. And that's basically refers to you're failing to collect outcome data from some individuals who were part of the original sample, right? So that could be because they move away or they decide to drop out of the survey, so you just no longer can collect data on them. This can be harmful because it reduces statistical power. Basically, when you have attrition, you're reducing the sample size because you can't use the people that dropped out of the survey because it might not be random who drops out, right? So if you include them, there could be selection bias. You obviously don't want to include them in the survey or analysis, I should say. And so you're effectively reducing sample size, and that reduces statistical power. We're going to talk more about power in a few minutes, but yeah, it can be harmful because then you won't be able to effectively estimate a true effect if there is one even. And then it can also bias results because you might be concerned that this creates selection bias. So your original sample is randomized and there's no selection bias in your estimates. However, if people drop out of the treatment group or control group, it might not be random why they drop out based on their characteristics. So maybe only the sickest kids drop out of a study because they die or they're too sick to go to school. That would definitely bias the results because then you would think that kids are healthier than they are because the sickest kids are not getting surveyed or are dead, right? So that would be bad analysis. And you really should make an effort if this happens to figure out why this attrition is happening. It's really not a concern if it's relatively low, like 1% or 2% of your sample, but if it's significant, like we saw in the STAR example was 50% attrition rate, that's huge, and you really need to know what's driving that. Oh my God. Okay. Yeah, so yeah, as I said before, even if the attrition rates are similar between the treatment group and the control group, it is still possible that there's selection bias or there's a different reason for dropping out of the treatment group compared to the comparison group, and that might still create bias. So it's really hard to say that there is equal attrition in both groups and therefore the resulting group is the same. Well, no, because it's still not random who drops out. So after that, you really do need to use some sort of method, which is an IV method, which we'll talk about in the IV section. But yeah, this isn't valid to analyze the results when you have such large attrition. Right, so an example would be you're evaluating a medication. Attrition due to death would be reduced in the treatment group, but attrition due to factors that the subject feels healthier and decides to stop complying with the experimental protocol may be increased in the treatment group. So maybe the control group you see attrition because kids are dying, and then the treatment group kids are dropping out because they feel good and they don't think they need it anymore. So you really do need to try and figure out why the attrition is happening, just to try and address the problems of selection bias. Okay, so one really good way to reduce attrition in our sample, it doesn't guarantee that there won't be attrition, is that you randomize within individuals that initially show interest in the program. So instead of just taking a random subpopulation of people and saying who gets treatment and who gets control, maybe you're better for if you say this program is happening and see who is interested in receiving the program. And then within that group of people who are interested in receiving the program, you then randomize. And that's thinking that basically if people want to enter the program, they're more likely to stay with it all the way through. So that is a really common method nowadays, just to only randomize within an interested population, just out of fairness and also to reduce attrition. And then also it helps for comparability because if you have an initial group and say some people really want treatment and others don't, well, then there could be differences in unobservable characteristics, right, between people who really want this program and who really don't. Maybe these people who want the program are more motivated, care more about their health, whatever, ambitious. So this is really nice to only look within people who show interest, because then you can think they might have similar unobservable characteristics that are motivating them to receive treatment. Yeah. Of course, it's always good too to keep really detailed data of the individuals in your survey. So even if they do drop out, you can somehow contact them afterwards to look into reasons of dropout. That could just help with your explanation of selection bias or not. Okay. And then finally, we have we have generally equilibrium effects. So that's kind of what I was talking about with the externalities. Basically, it doesn't necessarily have to be an externality, but I guess it is an example of one. So basically, your treatment effect has larger effects into the general equilibrium, and that would also harm our estimates if it affects our control group, right? So the problem is if we have general equilibrium effects, we really can't pick them up in our survey because we're only looking at the treatment group versus control group. We're not looking at a larger population, right? So that price example, for example, when the kids got free lunches in one school, the prices to go to school of other nearby schools went down. That would be a general equilibrium effect because not only the control group is affected, but everyone who goes to those other schools are also affected. That's what makes it really a general equilibrium effect over an externality, right? Is that not just the control group is contaminated, but the economy at large is somehow changed from this experiment. We do really want to avoid general equilibrium effects because, it would contaminate our estimates, and also you don't want to negatively affect anyone. It can be a positive general equilibrium effect, but it really does depend on the circumstance. All right, here's an example. So consider randomization of vouchers where students who win a voucher are offered a scholarship to a private school. So then we're comparing the outcomes for students who were given the voucher to go to private school against those who applied to get the voucher but didn't receive it. So this is like the partial or localized effect of the program between treatment and control groups. However, it's not to say that there wasn't a general equilibrium effect by introducing a voucher system onto the whole education system. This is in Colombia, right? So the general equilibrium effect could be affected by this. When you add vouchers, it basically changes the value of the good, right? Because we're saying, oh, you get this for free. So how would that change the value or the general equilibrium? Well, maybe it adds competition, basically increasing pressure on the public schools so that they improve their performance or lower their costs as well. right? So when there's a general equilibrium effect, and say it's the voucher example, and competition is improved, then these other schools in the control group would be improved too, just because they're more they face competition, so they improve, and so the outcomes of their students are also better. How does it differentiate from externalities? It differentiates because it's not necessarily only the control group that is spilled over onto, but also the whole economy. So it could have larger effects that basically impact the whole economy. I would say externalities. I mean, that's a good point. What's I guess yeah, I guess they're pretty similar, hey? When you actually think about it. Yeah, normally externalities we really only consider the control group, and that basically the control group is indirectly affected. But this general equilibrium effect is maybe not just the control group. Yeah. So yeah, for this example, the whole school system could be affected, which is making control schools improve their students' outcomes, and then our effects would be understated, right? Because then the control group's also improving the outcomes of their students when we really want them to just be staying constant. Yeah. Yeah, Nicholas says general equilibrium effects are more dynamic, I think. That's true too. They can last for a longer period of time. It's not just a one-time externality. It can definitely shift the way the whatever the economy is being affected. Okay, so another problem with implementation of randomization could be behavior effects. So these are called Hawthorne and John Henry effects specifically. So basically, when you have treatment to the treatment group and you're putting control in the control group, if they're aware that they're in this experiment, that might change their behavior, right? Um, so when we have changes in behavior among the treatment group, called the Hawthorne effect, while changes in behavior among the comparison group are called John Henry effects. Why do you guys think that changes in behavior would be problematic to our estimation? I was wondering what you guys think. Anyone? Yeah. Both Nicholas and Maria said we'll basically have problems in finding causality because we're not the differences in behaviors might be changing. So basically, if the control group, for example, behaves differently, based on the fact that they're in the control, their outcomes then might be different than what the outcomes would have been for the treatment in the absence of treatment, right? So they're basically indirectly affected by the treatment by changing their behavior. Um, so, for example, the treatment group, they might be grateful to receive a treatment, and they're also conscious. They know that their experimenters are watching them, and this might make them change their behavior just for the duration of this experiment. So, for example, maybe working harder or paying more attention or just being more involved in the project or treatment, whatever it is, than they would have normally been if it was just some sort of program implementation. And so if the treatment group is more engaged than they would normally be, then we might pick up a bigger treatment effect than say we were to roll this out to the public and we give this treatment. It's like an information campaign. And in our experiment, the treatment group were super attentive. They were listening to everything, writing down notes, really implementing it in their lives, which was just because they know they're an experiment. So then when we roll it out to the public, people don't care as much. They might not remember. They might not care to write things down. And so we might not see as big of a treatment effect in reality as we do in this program. And that's just because the behavior of the treatment group has changed, knowing that they're being watched or that they're an experiment. Okay. On the other hand, the control group could also be effective. So they might feel offended, for example, if they're in the control group not receiving treatment. That could alter their behavior. So for example, if it's this teacher experiment where some teachers are treated with improved strategies for teaching to their students, and they want to look at the outcome on student test scores, the teachers in the control group might be jealous that they're not being treated, and so they'll try harder to teach their students and be more effective, and that will increase their students' test score outcomes just because they're putting in extra effort. And so that competition from the control group would obviously not be reflected of the true counterfactual of the outcomes of the students in the absence of treatment, right? So they're being indirectly affected by the treatment. Nicholas says, but if that's how the program will work, it wouldn't be the systematic way in which individuals respond to the system. That's true. Like it could be systematic, like based on some sort of selection or characteristics. But you know, if that were true, then the treatment, well, I mean, even if that's true, the treatment group is in the treatment and the control group is in the control, right? So they're in different basically conditions. So maybe one person acts one way in the treatment group, so they're trying super hard to be impressive. But if they were in the control group, they might be bitter and try harder because they're in the control group. So, I mean, it's hard to say because each person is in a different group, and different groups can kind of create different behaviors. So it's not just as simple as randomizing. Yeah, no problem. Yeah, so I mean, it's really hard to say what behavior would be because maybe these teachers are become super competitive in the control group, but maybe they're also just like, I wasn't treated, I don't care, like I'm not gonna try at all, like it's no fair that I didn't receive this help, my students are gonna suffer, I'm just not gonna put in any effort, and hoping maybe that without putting in effort, the experimenters will see really bad test scores from their students, and so they'll feel incentivized to come to this group and give them help. So that could be another way it's affected too. It's really hard to say how behaviors will be affected by a treatment, but just knowing that they can be. Right, because of course behaviors are unobservable, so it's really hard to do much about. But really, within your research, just trying to have a good program design where maybe control groups aren't really informed about the treatment, or that it's not really, the treatment's not incentivizing treatment groups or control groups to act too far out of nature or what they normally would. So that could be less involvement, so not so, experimenters are less hands-on, so the individuals have time to be on their own and deal with the treatment on their own. and less watched, that might create them to act more naturally. So a good example of behavior effects, I think, is this Breza et al. Paper. It basically looks at the effects of wage inequality on productivity. Actually, what is the outcome? I actually can't remember the outcome, but I think it was productivity. And so basically to do that, they randomized a bunch of groups, where some groups all received the same wage, and other groups they had people one person receive a high wage, and one person receive a low wage, and one person receive a middle wage. Of course, there's problems with this because people aren't just going to act the same if they receive a high wage to a low wage, right? So obviously, if I receive a low wage, I may act bitter and try less hard than if I had received a high wage. And also, maybe I'm less likely to even show up for work. So if people don't come, that's attrition in your sample, and that could also be a problem for estimation. So yeah, one way to get around this, I think, would have been if afterwards they said that they would recompensate the people that receive low wage so that in the end everyone gets paid the same, and then maybe there's less incentive to slack off, but I don't know. Okay, so now we're going to go into power calculations. We kind of talked about it briefly about how power can be affected in our sample. For example, when we stratify and we look at the group level, it can be reducing our power. So now we need to think about what power is. Okay, so the power of the design is the probability that for a given effect size and a given statistical significance level, we will be able to reject the hypothesis of zero effect, right? So the power is the probability that will reject the null hypothesis when the null is wrong. So the probability of rejecting the null, so remember that the null is h naught equals 0, right? There's no effect. And that's when the null actually is different from 0. So power is good because it's telling us the probability of rejecting the null when there is actually an effect. So it's capturing a true effect when there is one. Right? So different things will affect the power of an experiment. Most importantly, sample size, I would say. Other things can affect it as well. So always, larger sample sizes are better, and it gives us more precise estimates of the population characteristics, and it will improve our power. So exactly how large do samples need to be for our impact evaluation? It really depends, and it depends on different factors, and we can basically determine that based on power calculations, right? Because it's telling us how large a sample size we need to be able to detect an effect when there is an effect there. So how large a sample we need to reject the null hypothesis when there is an effect, when the null is false. Okay. So it's really good because power calculations can indicate the minimum sample that's needed to conduct an impact evaluation and to convincingly answer these questions of interest. So of course we want to do power calculations just to know an optimal sample size. I mean, this isn't super important in retrospective studies necessarily because the data is already there. But if we're creating this experiment, a randomized experiment, and we want to create a sample, we want to make sure that we have enough people in our sample that if there is a true effect of our treatment, that we're able to capture it from our estimation. because if the sample's too small, we might not even be able to do that, even if the treatment is receiving an effect. Yeah, power calculations are good to assess whether existing data sets are large enough to conduct impact evaluations. They're good to avoid collecting too little data. Like if the sample is too small, you're not even able to detect a positive impact, even if there is a positive impact in reality. It's just not enough power, so you don't know it's there. Obviously, that's bad for policy recommendation, because then you could be recommending, no, don't implement this policy or eliminate this policy. It's not effective. Even if it is effective, you just don't know. And then also helping to make adequate decisions about sample size. Of course, we always want a larger sample because it's more accurate. But there is a cost involved with collecting more data, right? We need people to collect data. It takes time, it takes money. So we don't want to just collect an infinitely large data set. We want to know what the threshold is to be able to still find significant effects if there is, but without spending too much money on data collection. All right, so there is a trade-off there. Okay, so yeah, the basic principles of power calculation can be illustrated in a simple regression framework. So our regression standard is the OLS, where yi is a function of alpha plus beta times t plus epsilon I. So t would be the treatment dummy in this case. I know we normally do di, but yeah, this is the dummy if the group receives treatment, or the individual I receives treatment, I should say. And then as there's only one treatment, let's say a proportion of p of the sample is treated. So we have p individuals in our sample treated. And then now you can assume that for each individual, they were randomly sampled from an identical population. So the observations can be assumed to be IID with variance sigma squared. So then the variance of beta hat is given by the following equation. So you just have the variance beta hat is a function of your sigma squared over n, where n is the population. And then you also multiply that by the proportion of treated. So 1 over p, the proportion treated, and then 1 minus p is obviously the non-treated. And so that would be the formula for the variance of beta hat. And then in general, we're interested in testing the null hypothesis, H naught, and that is that the effect of the program is equal to 0, right? So there's beta is equal to 0. That's our null. Against the alternative hypothesis, H1, and that's beta is different from 0, right? So there is a true effect. So the significance level or size of a test, which is our alpha, represents the probability of a type 1 error. And a type 1 error is the probability we reject the null hypothesis when the null is true. Right? So oftentimes the type 1 error is chosen by the researcher and is usually fixed at 5%. And that would mean that you can be 95% confident in concluding that the program does have an impact. Yeah, type 1 errors are concerning for policymakers. Obviously, we're striving to implement effective policy. If we incorrectly estimate an ineffective policy by saying it's effective, that's a bad policy recommendation, right? We're saying, hey, implement this policy. We think it has positive treatment effects, whereas in reality it doesn't. On the other hand, the type 2 errors are also concerning. Recall that type 2 errors, you're failing to reject the null when the null is false. So you're saying there's no effect when there is one. So we also don't want type 2 errors, because then we're labeling policy as ineffective when it actually is, when we're just looking at a type 2 error. Okay. With respect to hypothesis tests, the power of the test is the probability we reject H naught when it is in fact false. So that's good, right? Like that's estimating the correct effect. So put in other words, it's the probability that we will detect a difference between the treatment and comparison group when one doesn't exist. Right? That's not saying that we're going to have perfect causality. It's saying that if there's a treatment effect, we'll be able to see it because we have enough data or power. Why power calculations matter for policy, we already kind of talked about this. But basically the purpose of power calculations, we want to determine how large a sample is required to avoid concluding a program has no impact when it in fact does have one. So that's a type 2 error. Okay, so the power of a test is actually equal to 1 minus the probability of a type 2 error, which is fairly intuitive because recall that the type 2 error is the probability you fail to reject the null hypothesis when the null is false, and then the power is the probability you fail to reject, no, you reject the null when the null is false, right? So we're saying the power is the probability you reject the null when there is an effect, and then the type 2 error is you don't reject the null, you say there's no effect, but there is an effect. I'm sorry, this is, I can't imagine learning this over Zoom. This is not fun to teach right now. So yeah, an impact evaluation has a high power of a type 2 error. That's unlikely to happen. Oh wait, sorry. Sorry, I'll say that again. An impact evaluation has a high power if a type 2 error is unlikely to happen, right? Because our power of a test is equal to 1 minus the probability of a type 2. Therefore, if the probability of a type 2 error happening is small, we'll have a high power. That's pretty intuitive. Okay, yeah, so when we have high probability of a type 2 error, it can be pretty harmful because it risks, basically we have the potential, we won't be able to estimate an effect when there is one. And then we're not, like, why would we research then if there is an effect and there isn't one? Why are we putting money into making research like this when it wouldn't matter anyways, right? So it is important to have a good power of your test because that means our research is purposeful. Okay, I'm just gonna leave you with this today. I'm gonna show you a really nice video on Monday, which will refresh us. But this is basically two distributions. So you can see here on the left side, it says effect size 0. And so this is the normal distribution around effect size 0. So this is equivalent to our null hypothesis, H naught equals 0. And then this distribution is around effect size beta. So say this is around the distribution of our alternate hypothesis, H naught is different from 0. And we're saying H naught then equals, or H1, what am I saying, equals beta, right? So we have two distributions, left and right. This is for our effect size, and this is for effect size equals 0. Okay, this T is our T statistic for alpha, right? Alpha is the size of our test. And so say that it's normally like 5%. So this is our T alpha. And you can see here, so say this is from 0 to 95. I guess this is two-tailed, so it'd be like 97.5. And then this is the 2.5% left in the right side tail. And then this is T1 minus K, where K is our power. So this is basically the T statistic for type 2 errors, right? So we want our type 2 errors to be small. And yeah, I guess this area right here is the intersection between where we have an effect size. So we reject the null hypothesis, right? And then this is the possible variation for beta. But we're out of time, so we'll talk about that more on Wednesday. Just try and look through the slides so far so you understand power calculations for the next class. Of course, we're not done yet, so we'll go over it more on Wednesday. Okay, if you guys have any questions about assignments or material, feel free to email me at any time. I'm available. Okay, goodbye.